Imagine 2 ordinary dice resting in your hand. Nothing special about them. 6 faces each, the pips worn a little smooth. Now, without doing any arithmetic at all, just feel your way toward an answer. If you roll them, are you more likely to get a total of 9 or a total of 10? Almost everyone feels those are the same. They are not. 9 can be built 4 ways. 3 and 6, 4 and 5, 5 and 4, 6 and 3. 10 can be built only 3 ways. 4 and 6, 5 and 5, 6 and 4. So 9 arrives slightly more often, and it has always arrived more often, and it will go on doing that quietly forever, whether or not anyone is watching. That is the whole subject in one breath. Counting the ways. However, and this is the part that never stops being strange, human beings had been rolling dice for something like 4,000 years before anybody wrote that down. We raised the pyramids. We predicted eclipses centuries ahead. We measured the size of the earth from shadows, and the entire time, in every one of those places, people gambled, and seriously, and often ruinously, and nobody thought to ask how often. Tonight we go slowly through what happened when they finally did. From knucklebones on a dirt floor, to 2 Frenchmen writing letters in the summer of 1654, to a curve that turns up underneath almost everything, to the question of whether the universe itself is rolling dice, or only looks that way from here. You do not need to stay awake for any of it. Drift off wherever you like. The counting will carry on perfectly well without you. Let's begin. Chapter 1. Start with the object itself, because it is older than almost anything else we still use. Before there were dice, there were bones. One bone in particular, the astragalus, which is the small knobbly ankle bone of a sheep or a goat sitting just above the heel. Take one out, clean it, dry it, and you have a little irregular lump with 2 rounded sides that it will never rest on, and 4 flattish sides that it will. Throw it, and it settles one of 4 ways. The 4 ways are not equally likely, because the bone is not symmetrical, and everyone who ever played them knew that in their fingers long before anyone could say it in numbers. People have been throwing these for a very long time. They turn up in graves, in the floors of houses, in the corners of temples, across Mesopotamia and Egypt and Greece and the Indus Valley. They are painted on tomb walls. They are carved into the sides of game boards, and the cubical die, the 6-sided kind you would recognize instantly, goes back at least 4,000 years, and probably further than that. So, for 40 centuries or more, human beings sat on floors and in courtyards and in the back rooms of taverns, and threw small objects that landed one way or another. They cared enormously about the result. They staked money on it, and land, and animals, and now and then themselves. And in all that time, as far as anyone can tell from what has survived, nobody wrote down the odds. That is worth sitting with for a moment, because it is not a story about people being slow. It is a story about a question that simply was not being asked, and there are good reasons why. Here is the first one. For much of that history, a thrown lot was not a random device at all. It was a channel. In a great many cultures, casting lots was precisely how you took a decision out of human hands and put it into someone else's. The bone fell as it fell because something intended it to, and if the fall is a message, you do not ask how often the message repeats. You ask what it means. Those are different questions, and the second one crowds out the first. The second reason is beautifully practical. The dice were bad. Archaeologists who have gone through large collections of surviving ancient dice, measuring them properly, have found that a great many of them are visibly lopsided, longer in one direction than another, with faces that are not quite square and pips drilled deep enough to shift the balance. Dice only become reliably close to true cubes rather late in the story, which means that if some clever person in the ancient world had worked out the theory and then rolled a real die 200 times to check, the numbers would have disagreed with them, and they would have concluded, quite reasonably, that they were wrong. And the third reason sits deepest. There was no habit of the question. Knowledge in the inherited picture meant certainty. Geometry was knowledge. Astronomy was knowledge. The behavior of a tumbling bone was the opposite of knowledge. And the idea that you could build something rigorous on top of something uncertain would have sounded like a category error. It took a long time for anyone to see that uncertainty has a shape and that the shape can be measured. You can let your shoulders drop here. There is nothing yet to hold on to. We are only setting the table. Now to the first person who wrote it down. His name is Girolamo Cardano, born in Pavia in 1501, the illegitimate son of a lawyer who happened to be a friend of Leonardo da Vinci. He grew up sickly and poor and difficult, was refused entry to the College of Physicians in Milan for years because of his birth, and then became, by sheer stubbornness, one of the most famous doctors in Europe. Kings sent for him. He also wrote on algebra, on mechanics, on medicine, on dreams, on his own faults, at enormous length, and he gambled, constantly. Dice cards, chess, for decades, by his own frank admission, sometimes to the point of losing everything in the house. Somewhere in the 1560s he wrote a short book about it, which we now call the Book on Games of Chance. It sat unpublished for the rest of his life, and for the better part of a century afterward, finally appearing in print in 1663. Long after he died in 1576, inside it, he does something nobody had done. He writes out what he calls the circuit, which is his word for the full set of things that could happen. All 6 faces of one die. All 36 ordered pairs for 2 dice. And then he says, in effect, that the chance of what you want is the number of ways it can happen set against the total number of ways anything can happen. A ratio. Favorable cases over all cases. That sentence is the foundation of everything that follows tonight, and it is sitting in a manuscript in a drawer between a passage on how to detect a marked deck and a long, anxious argument with himself about whether gambling is a sin. He gets things wrong too. When he tries to work out repeated throws, how likely a particular face is to show up at least once in several rolls, he reaches for the wrong rule first, then catches himself and corrects it, which may be the most human paragraph in the entire history of the subject. He is arguing with himself in the dark, with nobody to check his work. His life was not a gentle one. His eldest son was executed in 1560, and Cardano himself spent time imprisoned late in life over a book he should not have written. He kept working through all of it, and he kept writing about himself with an honesty that still reads strangely modern. Now, let me close the question from the beginning, because someone did finally answer it. Around 1620 or thereabouts, Galileo Galilei wrote a short piece on dice, apparently for a patron at the Medici court who liked to play. The gamblers had noticed something and could not explain it. Playing with 3 dice, they were sure from long experience that totals of 10 and 11 came up a little more often than 9 and 12. Only a little, but they had thrown enough to be certain. And the puzzle was this. If you sit down and list the sets of 3 numbers that add up to 9, you find 6 of them. If you list the sets that add up to 10, you also find 6. 6 and 6. So why is one of them turning up more often than the other? Galileo Galilei's answer is the whole trick of the subject, stated once and cleanly. The dice are separate objects. Even if they look identical, they are 3 different things, and each of them lands on its own face. So when you count, you must count the ways, not the recipes. A 2, a 3, and a 4 can arrive in 6 different arrangements. 3 3s can arrive in only 1. Do that properly for all 216 possibilities, and 9 happens 25 ways, and 10 happens 27. A gap of 2 out of 216. Small enough to be invisible in an evening, large enough to be obvious in a lifetime of playing. And that is exactly the same reasoning that made 9 beat 10 with the 2 dice in your hand at the start. Not because 9 is favored, only because there are more roads into it. 4,000 years of throwing, and the answer was always sitting there in the counting, waiting patiently to be noticed. Chapter 2. The counting was there. What was missing was a reason to care about it, and the reason, when it came, was money on a table in an unfinished game. The puzzle is called the problem of points, and it is easy to state and surprisingly hard to settle. 2 people are playing a game of pure chance, round after round, each round as likely to go one way as the other. They have each put in the same stake, and the agreement is that the first player to win a set number of rounds takes the whole pot. But something happens. A messenger arrives, the tavern closes, one of them is called away. The game stops partway through, and it will never be finished. The pot is sitting there. How do you divide it fairly? Keep it small so you can hold it in your head. Say the agreement was first to 3 rounds. Say they stop when one player has won 2 rounds and the other has won 1. So one of them needs a single round to take everything, and the other needs 2. Luca Pacioli, the Franciscan friar who wrote the great arithmetic textbook of 1494, the same man who set out double-entry bookkeeping for Europe, posed exactly this and answered it. His answer was to divide the pot in the same ratio as the rounds already won, 2 to 1. It feels reasonable. It is also wrong, and Niccolo Tartaglia saw why. Imagine the game is interrupted after a single round. One player has won 1, the other has won none. Pacioli's rule hands the entire pot to the first player on the strength of 1 round out of 3, which nobody would accept. Tartaglia offered a different rule and then said something rather lovely and honest, which is that, in his view, the question could not really be settled by mathematics at all and belonged to a judge rather than to an arithmetician. Girolamo Cardano got closer than either of them. He saw that what matters is not what has already happened, but what each player still needs. The past is finished. The money is about the future, but nobody could turn that into a method, and there the problem sat for 160 years. Then, in 1654, a French nobleman with a taste for gambling and for the company of clever people brought it to the right person. His name was Antoine Gombeau, and he went by the title Chevalier de Mer. He was a writer on manners and conversation, and he moved in the same Paris circles as the mathematicians, and he had two things bothering him. The second one was the problem of points. The first was about dice, and it is worth a moment because it shows how easily good reasoning goes wrong. He knew, from long experience at the table, that betting on getting at least 1/6 in 4 throws of a single die was a bet worth taking, slightly better than even, and he reasoned that the same should hold for a longer version. With 2 dice, a double 6 comes up once in 36 throws rather than once in 6, so the game should be 6 times longer. 4 throws becomes 24 throws. Same bet, scaled up, except it was not the same bet, and he could feel it. The 24 throw version kept losing. He was right, and his reasoning was wrong. Work it out slowly. The chance of missing a 6 on 1 throw is 5 in 6. Missing it 4 times in a row is 5/6 multiplied by itself 4 times, which comes to a little under 49 in 100. So the chance of getting at least 1/6 is a little over 51 in 100, just on the good side of even. For the double 6, the chance of missing on 1 throw is 35 in 36, and missing it 24 times running comes to a little under 51 in 100. So, getting at least 1 double 6 is a little over 49 in 100. Just on the wrong side, 2 bets that scaling says should be identical, landing on opposite sides of the line, separated by about 2 chances in 100. That is a difference you would never notice in an evening, and could not fail to notice in a career. The story is usually told as though he detected it purely at the table, and it may have been tidied a little over the centuries. But the puzzle is real, and the reasoning error is exactly the kind everyone makes. Proportions do not survive being multiplied together. They shrink in a way that feels wrong to the gut. So he brought his questions to Blaise Pascal, who was then 31, already famous for a calculating machine he had built for his tax collector father, and for work on air pressure and on conic sections. Pascal could not settle the problem of points alone. So he wrote to a lawyer in Toulouse. Pierre de Fermat was a magistrate by profession, and one of the finest mathematicians alive by inclination, a man who did his best work in the margins of other people's books, and rarely published anything. Over the summer of 1654, the two of them exchanged a handful of letters, and inside those letters an entire way of thinking about the world comes into being, almost as a side effect. Fermat's method is beautifully blunt. Do not reason about the interrupted game. Instead, Imagine playing out every possible way the rest of it could have gone, and count. Go back to the small version. One player needs one more round, the other needs two. At most 2 more rounds would settle it. So write down every way those 2 rounds could fall. The first player could win both. The first could win the first and lose the second. The first could lose the first and win the second. Or the first could lose both. 4 possible futures, each as likely as any other. In 3 of those 4, the player who needed only 1 round gets it. In just 1 of the 4, the other player takes both rounds and the pot, 3-1, not 2-1. Pascal had an objection, and it is a good one. In 2 of those 4 futures, the game would actually have stopped early. If the leading player wins the very next round, nobody would bother playing another. So, why are we counting rounds that would never be played? Fermat's answer is the quiet hinge of the whole thing. It makes no difference. Play them out anyway. The extra rounds change nothing about who ends up winning, and keeping them in makes every future equally weighted, which is exactly what makes the counting honest. Pascal thought about it and agreed, and then found his own way to the same answers by working backwards from the end of the game, instead of forwards from the middle. What those letters really established is not an answer about card tables. It is a principle. The fair value of an unfinished situation is decided by what would probably have happened, weighted by how likely each outcome was. The past has no claim on the money. The future does, even though it never arrives. There is a small human coda. That same year, on a November night, Pascal had an intense religious experience, wrote an account of it on a scrap of parchment, and sewed it into the lining of his coat, where it was found after his death. He turned away from mathematics for most of the rest of his short life. He died in 1662, not yet 40, and in the notes he left behind, arguing about faith, he used the very tool he had just built. Weigh each outcome by its chance and by what it is worth. It is the first time anyone had applied the arithmetic of gambling to a decision that had nothing to do with a game. If your attention is drifting by now, that is entirely allowed. Let it go where it wants. 2 men wrote letters for one summer, and the arithmetic they worked out has been sitting quietly underneath everything ever since chapter 3. So let us slow down and say plainly what a probability is, because the whole rest of the night rests on it, and it is simpler than people expect and stranger than they expect at the same time. Take any situation where you do not know what will happen. Write down every separate thing that could happen, so that exactly one of them will turn out to be the case. That list is the ground you stand on. For a coin, the list has 2 entries. For 1 die, 6. For 2 dice, 36, because you count the first die's face and the second die's face as separate facts, exactly as Galilei insisted. Now, if every entry on that list is as likely as every other, the probability of anything you care about is simply how many entries on the list satisfy it, divided by how long the list is. That is all Girolamo Cardano's ratio was. Favorable cases over all cases, 2 rules follow immediately, and they are worth having because between them, they cover a great deal of ordinary life. If you want either of two things that cannot both happen, you add. The chance of rolling a 1 or a 2 on a die is 1/6 and 1/6, which is 1/3. If you want both of two things that have nothing to do with each other, you multiply. The chance of a coin landing heads twice running is 1/2 of 1/2, which is 1/4. Adding grows things. Multiplying shrinks them. And almost every misjudgment anybody makes about chance comes from muddling those two, or from applying the multiplying rule to two things that secretly do have something to do with each other. We will come back to that. But notice the phrase I slipped past a moment ago. If every entry on that list is as likely as every other, that little clause is doing an enormous amount of work, and it is quietly circular, because to say two things are equally likely is already to say something about probability. Nobody could see a way out of that for nearly 300 years, and we will come back to it much later tonight when we meet the man who finally cut the knot. For now, hold it lightly. The dice are fair because they are symmetrical, and the coin is fair because it is a disc, and that will do. Now to the man who turned the letters into a book. Christian Huygens was Dutch from a distinguished family in The Hague, and he was the leading physicist of his generation. He built better telescopes than anyone, found the rings of Saturn and its largest moon, and invented the pendulum clock, which took timekeeping from an error of 1/4 of an hour a day down to seconds. In 1655, he visited Paris, and he heard the talk. Everyone was discussing the problems that Blaise Pascal and Pierre de Fermat had been passing back and forth. But nobody would show him the letters, or perhaps nobody had them. He got the questions without the answers, so he went home and worked them out himself, and then he wrote a small treatise, first in Dutch and then translated into Latin by his old teacher, and it was published in 1657, 16 pages or so. It is the first printed work on probability that anyone ever produced, and for the next 50 years it was how the subject was taught, and Huygens did something the letters had not quite done. He put a single idea at the center and built everything from it, and the idea was value. Suppose someone offers you a game. You roll one ordinary die, and they pay you a coin for every pip showing. 1 coin for a 1, 6 coins for a 6. What is that game worth before you roll it? Add up what you could win, weighted by how likely each is. 1/6 of a chance at 1 coin, 1/6 of a chance at 2, and so on to 6. The answer comes out at 3.5 coins, which is a strange number because there is no face on the die that pays 3.5. It is not what you expect to get. You will never once get it. It is the fair price of the game, the amount at which neither side is being taken advantage of, and over many plays, it is what the average settles toward. Huygens called it expectation, and the name stuck, and it is slightly misleading in every language it has ever been translated into. Expectation is not a prediction. It is a price. That single move is what lets probability escape the card table. Once you can put a number on the value of an uncertain thing, you can insure a ship or price a pension, or decide whether a trial is worth running. Everything practical that follows comes out of those 16 pages. Now, one honest warning about the whole enterprise. Before we go on, the theory is easy. The counting is murder. Almost every hard problem in this subject is hard, not because the reasoning is subtle, but because listing all the possibilities is enormous. Which is why the next thing Blaise Pascal did in a work published after his death in 1665 was to lay out a tool for counting quickly. He called it the arithmetic triangle. Picture it, a single number at the top. Below it, two numbers, each a 1. Below that, a row where every number is the sum of the two sitting just above it, with ones down both edges. Then another row and another. The rows grow, and every number in them is just an addition away from the row before. And those numbers turn out to answer a question that comes up constantly, which is how many different ways you can choose a handful of things out of a pile without caring about order. How many ways to pick 2 people from 5? How many hands of 5 cards from 52? The triangle simply tells you, and you never have to list anything. Pascal did not invent it, and he never claimed to. The same triangle had been written down in India, in commentaries on ancient work about the rhythms of poetry, in Persia by mathematicians including Omar Khayyam, who is better known now for his verses, and in China, where it appears in a book from 1261 and is still called Yang Hui's triangle. Several civilizations found the same pattern for entirely different reasons, and none of them knew about the others. Let me leave you with one result you can carry around, because it is the friendliest surprise in the subject. Put 23 people in a room. What is the chance that 2 of them share a birthday? The feeling is that it should be small. 23 people against 365 days. But it is a little over 1/2. More likely than not. The reason is that you are not asking about people. You are asking about pairs, and pairs multiply fast. 23 people can be paired up in 253 different ways, and every one of those pairs is a separate chance to match. Bring the room up to 57 people, and the chance is about 99 in 100. And here is the part that makes it click. If you asked instead for someone to share your birthday specifically, the exact date you were born, you would need a room of about 253 people before it was more likely than not. 253 again. The same number appearing on both sides of the puzzle, which is the kind of small elegance this subject hands you when you are not looking for it. If your eyes are heavy, let them close. The triangle keeps adding itself up, row after row, all the way down. Chapter 4. There is a problem hiding under everything we have said so far, and it is time to name it. Every example has been a die, a coin, a card, objects made deliberately symmetrical, so that we could say the 6 faces are equally likely without having to check. That is a lovely place to start and a very small place to stay, because almost nothing in the world is a die. What is the chance that it rains here tomorrow? What is the chance a person of 40 lives another 20 years? What is the chance this batch of grain is spoiled? There is no symmetry to appeal to. You cannot look at the situation and count 6 equal faces. All you can do is watch what happens over and over and try to learn the true proportion from the observed one. But that raises a question that had never been asked properly. If you watch 1,000 times and see a thing happen 300 times, how confident are you allowed to be that the underlying truth is close to 3 in 10? Does watching more actually help? And if so, by how much, and how much watching is enough? The man who answered that spent 20 years on it and died before he finished. Jacob Bernoulli was born in Basel in 1655 into a family of merchants who produced, over 3 generations, one of the most gifted and most quarrelsome collections of mathematicians in European history. His father wanted him in the church, so he studied theology to keep the peace and mathematics in private, and when he was finally free to choose, he adopted a personal motto that translates roughly as, "Against my father's wishes, I study the stars." He and his younger brother, Johann Bernoulli, spent much of their adult lives publicly attacking each other's work, which was a waste, and neither of them could stop. The book he was writing is called The Art of Conjecturing. He worked on it from around the mid-1680s. He kept refining and rewriting the last part, which was the part that mattered to him, and he died in 1705 with it unpublished. It sat for 8 more years until his nephew Nicolaus Bernoulli finally saw it into print in 1713. Inside it is a result Bernoulli himself called the Golden Theorem, which is not the kind of thing modest people say about their own work, and in this case he had earned it. We call it the law of large numbers. Here it is in plain speech. Suppose there is some true, fixed, unknown proportion sitting behind a repeatable event. Choose how close to it you want your estimate to be. Choose how certain you want to be of landing that close. You may set both of those as demanding as you like. Bernoulli proved that there is always some number of trials that gets you there. That sounds obvious until you notice what it is doing. It is the bridge between the world of dice, where you reason from the known truth outward to what you will see, and the world of everything else, where you have only what you have seen and want to reason back toward the truth. It says the bridge exists. It says that patient watching genuinely converges on reality. And it says how the 2 dials, closeness and confidence, trade off against each other. And then Bernoulli did the honest thing, which was to work out an actual number and to be disappointed by it. He asked what it would take to be confident at odds of 1,000 to 1 that his estimate sat within a narrow band of the truth for a case where the true proportion was 3 in 5. The answer he calculated was more than 25,000 trials. He remarked that this was a larger number of observations than there were people living in his city. You can hear the deflation in it. He had proved that certainty was reachable in principle, and the price in practice was ruinous. Later mathematicians found much tighter bounds, and the real requirement is far smaller than his estimate. But he was the first to see that the question had a shape, and he refused to pretend the answer was cheap. That is a decent place to let your breathing settle for a moment. Nothing here needs you alert. The numbers are patient. Now, because we have the law in front of us, let us use it to take apart the most persistent mistake anybody makes about chance. You have seen a coin land heads 5 times running. What about the 6th? The feeling is almost impossible to shake. Tails is due. The coin has been running a debt and it must be paid. And the law of large numbers seems to back you up, because it says the fractions will even out in the long run, so surely something has to pull them back. The coin has no memory. It is a piece of metal. It does not know it landed heads 5 times, and it would not care if it did. The 6th flip is exactly 1/2, precisely as the first one was. The story usually told about the worst version of this happened at a roulette table in the Monte Carlo casino in 1913, when the ball is said to have landed on black 26 times in a row. As the run went on, the crowd bet more and more heavily on red, convinced that the correction was overdue, and lost a great deal of money. Every single spin was as independent as the one before it. So how can both things be true? How can the fractions settle down toward 1/2 if no individual flip is ever nudged toward it? The answer is quietly beautiful, and once you see it, you never lose it. The imbalance is not corrected. It is diluted. Suppose after 100 flips you are 10 heads ahead. That is a 10% excess, and it looks like a lot. Now keep flipping. Nothing in the coin works to erase those 10. On average, that surplus of 10 just sits there, and in fact, the raw gap between heads and tails tends to grow larger as you go, not smaller. But the total keeps growing much faster. After 1,000,000 flips, being 10 ahead is a rounding error. The fraction slides toward 1/2, not because the excess is repaid, but because it is drowned. The past is never canceled. It is only outnumbered, which is, if you want it to be, quite a kind thing for a piece of mathematics to say. Nothing goes back and undoes what happened. It simply becomes a smaller and smaller part of a longer and longer story, until it hardly shows at all. Chapter 5. Now we come to the shape, and I want to take it slowly, because this is the moment when the subject stops being about games and starts being about everything. Begin with something you can picture. Take a fair coin and flip it 100 times and count the heads. You will not get 50. You will get 46 or 53 or 49. Do the whole 100 flips again, and you get another number near the middle. Do it 1,000 times over, and make a little pile for each result, stacking them side by side. What grows in front of you is a hill, tallest in the middle, sloping away evenly on both sides, thinning out toward the edges but never quite stopping. 50 is the most common single answer, but only just. The hill is smooth, and it has a particular smoothness that does not depend on you at all. The first person to describe that hill precisely was a refugee working out of a London coffee house. Abraham de Moivre was born in France in 1667 into a Protestant family at a time when that was becoming an expensive thing to be. When the toleration granted to French Protestants was revoked in 1685, he was imprisoned for a period and then left the country for good. He arrived in London in his 20s and never went home. He was, by common agreement, brilliant. He became a close friend of Isaac Newton and of Edmund Halley, and there is a story, probably improved in the telling, that Newton took to answering mathematical questioners by saying they should go and ask de Moivre, who knew these things better than he did. And for all of that, he never obtained a university position anywhere in England because he was a foreigner. and he stayed poor his entire life. So he worked in a coffee house on St. Martin's Lane at a fixed table, and for a small fee he would solve problems for anyone who came in. Gamblers wanting odds, insurance underwriters wanting to price the life of a man of a certain age. He tutored, he calculated, he wrote the best book on chance of the era called The Doctrine of Chances, and dedicated it to Newton, and in 1733. In a short private paper that he later folded into that book, he did the thing that mattered. The problem was practical. If you wanted to know the chance of getting, say, between 45 and 55 heads in 100 flips, you had to add up 11 separate terms from the arithmetic triangle, and the numbers involved were monstrous. For 1,000 flips, it was hopeless by hand. So he looked for a smooth curve that would sit on top of those stacked piles and let him find the area underneath instead of adding the bars one by one. He found it. He worked out its shape exactly, and he worked out the natural unit of width for it, the typical distance from the middle, which we now call the standard deviation, and he calculated how much of the hill lies within one of those steps of the center, and got the number we still use, which is a little over 2/3. He published it, and it made very little noise, and he died in 1754. Then the same curve started appearing in places that had nothing to do with coins. Carl Friedrich Gauss was studying a different problem entirely. In 1801, an Italian astronomer had spotted a small new object between Mars and Jupiter, the one we now call Ceres, tracked it for about 40 nights, and then lost it in the glare of the sun. Nobody knew where it would come out again. Gauss, then 24, took the handful of imperfect observations, invented most of the necessary mathematics on the way, and predicted where to look. Astronomers pointed their telescopes there at the end of the year, and found it. The heart of that work is a question about errors. Every measurement is slightly wrong. The wrongness comes from 100 tiny independent causes: a wobble in the mount, a shimmer in the air, a moment's fatigue in the eye. What shape do those errors take when you pile them up the same hill? In 1809, Gauss set it out formally as the law of errors, and it has carried his name ever since. And then Pierre-Simon Laplace, in 1810, explained why it keeps happening. And this is the result that makes the whole thing feel almost unreasonable. Take a great many small independent effects. It does not much matter what they are. They do not have to be coins, or errors, or anything alike. Add them all together. The total near its center takes that same shape, always. The individual pieces can be lopsided, oddly distributed, wildly different from one another, and the sum still slides toward the same smooth hill. This is called the central limit result, and it is the reason the curve is everywhere. Human height is the sum of a great many small contributions from many genes and from nutrition and from childhood illness, and so heights pile into a hill. Measurement error in a laboratory, the scatter of shots around a target, the total sales of a shop across many independent customers, all the same shape, arriving for the same reason. That is a large idea, so let it just sit there for a while. You do not need to do anything with it. You are allowed to fall asleep on the slope of the hill. Now, a caution, because this is where the story has done some harm. Adolphe Quetelet was a Belgian astronomer who turned his instruments on people. In the 1830s and 40s, he gathered data on human bodies and human behavior and found the same curve again and again. Chest measurements of several thousand Scottish soldiers piled into a hill, heights of French conscripts, rates of marriage, of crime, of suicide, steady year after year across whole populations, even though no individual could be predicted. He was genuinely onto something, and he was the first to insist that societies have measurable regularities. But he also invented a character he called the average man, placed him at the peak of the curve, and treated him as an ideal rather than an arithmetic artifact, which meant that distance from the middle became, in that framing, a kind of defect. That idea traveled badly through the century that followed, and we will meet its consequences again shortly. The other caution is mathematical, and it matters more than people realize. Not everything is a hill. The central limit result needs its ingredients to be independent and to be added together, and it needs no single one of them to be able to dominate all the others. Break any of those conditions and the shape changes completely. Wealth is not a hill because money grows by multiplying rather than by adding. City sizes are not a hill. Earthquake energies are not. Sudden moves in financial markets are not. Because on a bad day, everything moves together and independence collapses exactly when you need it. In those cases, the extreme events are far more common than the smooth curve would ever suggest, and treating them as though they were rare has cost real people a great deal. So the hill is the deepest pattern in the subject, and it is not a law of nature. It is what you get under certain honest conditions, and part of understanding it is knowing when those conditions are not there. But when they are there, it appears without fail, in coins and in stars and in the chests of soldiers, and nobody put it there. Chapter 6. Let us come down off the hill and sit somewhere smaller and warmer, because the next idea is a quiet one, and it is about how a mind changes. Start with something ordinary. You are in bed, and you hear a sound in the house. Before you heard it, you had some vague sense of what might be happening in the rooms below. Nothing in particular. Now the sound arrives, and your sense shifts, not all at once, and not to certainty. The sound is more like the boiler than like anything else. So the boiler moves up, and the other possibilities move down, and within a second or two you have resettled. You did not start from nothing. You started from what you already believed, and the new information moved it. That is the whole of what we are about to describe, and you have been doing it your entire life. The technical name for the piece underneath it is conditional probability. It is the chance of something, given that you already know something else. And notice how much of ordinary reasoning is that and only that. The chance of rain, given that the sky is that particular gray. The chance a letter matters, given the envelope it came in. Everything up to this point in the night had been running in one direction. You know the cause, the die is fair, and you work out the effects, what you are likely to see. That direction is comfortable because the cause is given to you. Real life almost never works that way. Real life hands you the effect and asks about the cause. You have the symptom, not the disease. You have the reading, not the true value. You have the sound in the house, not the reason for it. You are always standing downstream. Looking up, the man who first wrote down how to walk back upstream was a minister in a small English spa town, and he never published it. Thomas Bayes was probably born in 1701, though the record is thin enough that even that is not certain. His family were Presbyterians outside the established church, which, in that period, closed the English universities to him, so he studied in Edinburgh. He became the minister of a chapel in Tunbridge Wells and stayed there for most of his working life. He was elected to the Royal Society in 1742, most likely on the strength of an anonymous pamphlet he had written defending Isaac Newton's calculus against a philosopher who had attacked its logical foundations. He published almost nothing else. There is no portrait of him that anyone can vouch for. The picture that circulates is probably somebody else. He died in 1761, and among his papers was found an essay he had never sent anywhere. His friend Richard Price, a moral philosopher and a serious thinker about insurance and public debt in his own right, went through those papers, understood what he was holding, wrote an introduction to it, and read it to the Royal Society in 1763. The essay sets up a small scene that you can see clearly. Imagine a flat table. Someone rolls a ball across it and lets it come to rest, and you are not allowed to look. All you know is that it stopped somewhere on the table and that no place was favored over any other. Now they roll a second ball and they tell you only one thing, which is whether it stopped to the left or to the right of the first one. Then a third ball and the same single word. Then a fourth. After a run of these reports, what can you say about where the first ball is? You can say a great deal, and that is the point. If most of the later balls came down to the left of it, the first ball is probably far over to the right. Every report narrows things a little. None of them ever gives you certainty, and crucially, you can attach numbers to what you now think honestly derived, starting from a state of knowing nothing at all. Bayes had built a machine for reasoning backwards, from what you have seen to what is probably behind it. The rule that carries his name works in 3 motions, and it is worth having in plain speech. Start with what you believed before the new evidence arrived. Then ask, for each possibility you are entertaining, how well that possibility explains what you have just observed. Then let the possibilities that explain it well grow, and the ones that explain it badly shrink in exact proportion. Evidence does not replace your beliefs. It reweights them. And how far you move depends on 2 things together: how surprising the evidence would be under each explanation, and how plausible each explanation was to begin with. Ignore the first, and you learn nothing. Ignore the second, and you will believe almost anything. That second half is where nearly all the trouble in the world comes from. And we are going to spend the next part of the night on exactly that mistake. Bayes never saw any of this happen. He had been dead 2 years when it was read out, and the essay made very little impression at the time. The person who made it matter was Pierre-Simon Laplace in France, who arrived at the same idea independently in the 1770s, and then spent decades building it into something enormous. He used it to estimate the mass of Saturn from the wobbles it produced in other bodies. And, in a move that was well ahead of its time, he stated how confident he was in his own answer and said what odds he would give. Later astronomers found he had been just about right. He also went through the birth registers of Paris, tallying boys and girls, and concluded that slightly more boys are born than girls, and that the excess was far too persistent to be a fluke, which it is and which nobody had established before. Then the method fell out of fashion for the better part of 2 centuries, and it fell hard. The objection was that in order to start reasoning, you have to say what you believed beforehand, and that felt like smuggling opinion into science. The whole apparatus was treated by many as slightly disreputable. It survived anyway, mostly by being useful to people who had a real problem and no other tool. It was used in artillery and in actuarial work. During the Second World War, it was used at Bletchley Park by Alan Turing and his colleagues to weigh fragments of intercepted German naval traffic, one small piece of evidence at a time, accumulating just enough to be worth acting on. That work stayed secret for decades afterward. So, for a long time, the people arguing about whether the method was respectable did not know. It had already helped decide a war at sea. It came back properly in the second half of the 20th century, once machines existed that could do the arithmetic, and it is now everywhere. It is in the software that filters unwanted mail. It is in how a search for a lost vessel is directed to the next square of ocean. It is in how a spacecraft works out where it is. If you are drifting now, drift. There is nothing to solve here. Only a minister in Tunbridge Wells writing something down for himself, working out how a reasonable person ought to change their mind, and then putting the paper away in a drawer where it waited for him to be gone. Chapter 7. We left a mistake sitting on the table, so let us pick it up gently, because it is the single most consequential error anyone makes with these ideas, and it catches everybody, including the people who ought to know better. Here is the shape of it. You have some test, some signal, some clue. You know how reliable the clue is. And then you use that reliability as if it were the answer to your actual question, when it is the answer to the reversed one. Let us walk through it with round numbers, and I want to say clearly that the numbers I am about to use are invented for the sake of arithmetic. They are not describing any real condition or any real test. They are chosen because they are easy to hold while half asleep. Imagine a condition that affects one person in 1,000. Imagine a test for it that never misses. If you have the condition, the test always says so. And imagine that the test raises a false alarm in 5 out of every 100 healthy people, which would be a fairly good test as these things go. You take the test, and it comes back positive. How worried should you be? The gut says something close to 95 in 100. It feels like the test is right almost all the time, so it is probably right about you. Now count instead Take 10,000 people and run all of them through it. Of those 10,000, about 10 actually have the condition. The test catches all 10. So we have 10 true positives. The other 9,990 are healthy. 5 in 100 of them will get a false alarm anyway, and 5 in 100 of 10,000 is about 500 people. So around 510 people have just been told they tested positive, and only 10 of them have anything wrong, which means that a positive result on these invented numbers corresponds to a chance of roughly 1 in 50, not 95 in 100, 1 in 50. Nothing about the test was misrepresented. It really does catch everyone who has the condition. The trouble is that the healthy group is so enormous that even a small error rate applied to it produces a flood of false alarms that swamps the small number of real cases. This is exactly the inversion Thomas Bayes was writing about. The chance of a positive result given that you are ill and the chance of being ill given a positive result are two entirely different quantities, and the second one depends on how many people were ever ill to begin with. That starting proportion is called the base rate, and forgetting it is the great modern error. Real screening programs are designed by people who understand this perfectly well, which is why a first positive is usually followed by a second and better test rather than by a diagnosis. But the structure of the mistake is worth carrying with you because it turns up far outside medicine, in security alerts, in fraud detection, in any situation where you are hunting for something rare. Now let me give you the other famous one, the one that caused an actual public argument. There was an American television game show called Let's Make a Deal, hosted for many years by a man named Monty Hall, and the puzzle took his name, though he had nothing to do with inventing it. It first appeared in print in a letter written in 1975 by a statistician called Steve Selvin, but it became notorious in 1990 when Marilyn Vosavant put it in her weekly magazine column. Here is the situation. 3 doors. Behind one of them is a car. Behind each of the other 2 is a goat. You choose a door and you do not open it. The host, who knows exactly where the car is, now opens one of the 2 doors you did not pick and shows you a goat. He always does this. He always opens a door, he always reveals a goat, and he always makes the same offer, which is this: you may stay with your original door, or you may switch to the remaining unopened one. Should you switch? Marilyn Vos Savant said, switch. And she was right, and the response was extraordinary. She received something on the order of 10,000 letters, telling her she had got it wrong, and a substantial number of those came from people with doctorates in mathematics and statistics, some of them quite rude about it. It ran on for months in print. Here is why switching wins. When you first chose, you had 1 chance in 3 of being right. That is fixed, and nothing the host does afterwards can possibly tell you anything about your own door, because he was always going to open a goat door no matter what you picked. Your door was right 1 time in 3 at the start, and it is still right 1 time in 3 now. So, the remaining 2/3 have to be somewhere, and there is only 1 other door left. All of that 2/3 is now sitting behind it. If that still feels slippery, stretch it out. Imagine 100 doors instead of 3. You pick one, with one chance in 100 of being right. The host then opens 98 other doors, all goats, leaving your door and one other. Would you stay with the door you chose blindly out of 100? Or would you take the one door the host carefully left closed while opening every single other one? Nobody hesitates at 100 doors. It is the same puzzle. There is an honest footnote, and it is the reason so many clever people dug in. The answer depends completely on the host's rules. If he opens a door at random and happens to reveal a goat, the answer changes. If he only offers the switch when you have already chosen the car, switching is a disaster. The version printed in the magazine did not spell out those rules, so a great many objectors were solving a different and perfectly reasonable puzzle. The lesson underneath is real. What you can conclude from what you are shown depends entirely on the procedure that decided what you would be shown. There is a story that the mathematician Paul Erdos, who was one of the most prolific in history, refused to accept the answer when a friend explained it and remained unconvinced through several explanations, and only gave way after being shown a computer working through the outcomes over and over, which I find genuinely comforting, and I hope you do too. If it takes a great mathematician several passes and a simulation, then you are not required to feel it in your bones tonight, or ever. Understanding here is a matter of counting carefully, not of being clever. Let the puzzles go now. The doors will still be there in the morning, and behind 2 of them, patiently, the goats. At Chapter 8, there is a force that seems to operate in the world, and a great many people believe in it, without ever naming it. It is the sense that things which go unusually well tend to be followed by things going worse. That the athlete who has an astonishing season is likely to have a disappointing one next. That the second book is never as good as the first. That the moment you praise a child for doing something beautifully, they will do it badly the next time. That pattern is real. You are not imagining it, but it is not a force, and nothing is causing it. And once you see where it comes from, you will notice it everywhere for the rest of your life. The man who found it was looking for something else entirely. Francis Galton was born in 1822 into a wealthy English family, a half-cousin of Charles Darwin, and he was one of those Victorians who could not stop measuring things. He made the first proper weather map. He worked out that fingerprints could identify a person, and that they do not change with age. He invented the statistical questionnaire. He was tireless, inventive, and, as we will come to, badly wrong about the most important thing he believed. In the 1870s, he was growing sweet peas. He wanted to see how a trait passes from one generation to the next, so he took seeds of carefully sorted sizes, planted them, and weighed what they produced. The large seeds gave offspring that were large, but not as large as their parents. The small seeds gave offspring that were small, but not as small as their parents. Everything had drifted in toward the middle. He found the same thing when he moved on to people. In a paper published in 1886, working from the heights of hundreds of families, He showed that very tall parents have tall children who are, on average, a little shorter than they are, and very short parents have short children who are a little taller. He called it regression toward mediocrity, using the word mediocrity in its old neutral sense of the middle. His first thought was that this must be a biological pull, some tendency of a species to hold itself to type, resisting drift toward extremes. And then he noticed the thing that undid that explanation. It runs backwards too. If you start with unusually tall children and look up at their parents, the parents are also closer to the middle than the children are, both directions. But a biological force acting through inheritance can only run forwards in time. Whatever this was, it was not being carried by the seeds. Here is what it actually is, and it takes about a minute to see. Any measurement of anything is made of two parts. There is the real, stable underlying quantity, and there is everything else, the noise, the weather that day, the mood, the luck, the sampling, the accident. Now think about who ends up at the very top of a list. To be at the extreme end, it helps enormously to be genuinely exceptional, but it also helps to have had things go your way. The people at the top are, on average, both truly good, and having had a good run, the genuine part stays. The lucky part does not repeat, because luck is not a property of the person. It is a property of the occasion. So when you measure again, the real quality is still there, and the fortunate accident is gone, and the number comes down. Not because anything happened to them, because the second measurement is being asked to reproduce something that was never theirs to keep, and the whole thing works identically at the bottom. The very worst performances contain real difficulty plus a stretch of bad fortune, and the bad fortune does not repeat either, so the next measurement improves. Galton built a machine to show this, and it is one of the loveliest objects in the history of the subject. He called it the quincunx, a tall, narrow box with a glass front, and inside it rows of small pins arranged in a staggered grid. You pour lead shot in at the top. Each pellet strikes a pin and goes left or right, then strikes another and goes left or right again 20 times over, and lands in one of a row of slots at the bottom. Every individual pellet's path is unpredictable, and every single time you run it, the pellets pile up in the slots, in the same smooth hill we met earlier, tallest in the middle, thinning at the edges. You can watch the central limit result happen in about 4 seconds, with your own eyes, in a wooden box. Let your eyes close for this next part if they want to. You do not need to look at anything. The consequences of regression are all around you once you have the idea. Daniel Kahneman, working with flight instructors, was told firmly by them that praise does not work and criticism does. Their evidence was direct. When a trainee flew a maneuver beautifully and was praised for it, the next attempt was usually worse. When a trainee flew badly and was shouted at, the next attempt was usually better. They had watched this happen for years. Every bit of that is exactly what regression predicts, whether or not the instructor says a single word. An exceptionally good landing was partly luck, and the next one will be closer to ordinary. An exceptionally bad landing was partly bad luck, and the next one will be closer to ordinary. The instructors had been taught by chance itself to believe that shouting works. The same illusion sits inside a great deal of medicine, education, and management. Any treatment given to whoever is doing worst will look effective. Any program that selects the very best performers and then measures them again will look like it has damaged them. This is precisely why serious trials use a control group, so that the improvement that would have happened anyway can be subtracted out. It also explains the small superstitions, the cover jinx, the sophomore slump, the difficult second album. Nothing is punishing success. There is simply nowhere to go from an extreme, except back toward the middle. Now the honest part about Galton, which I do not want to skip. He coined the word eugenics in 1883, and he founded the movement around it, and he spent the last decades of his life arguing that human breeding should be directed. Those ideas were taken up in the 20th century and used to justify sterilization programs and worse. In many countries, against real people who had no say in it. The statistical tools he built are genuinely his, and they are used every day by people working toward entirely different ends. Both of those things are true, and it seems better to say so plainly than to tell the story with the difficult half removed. What he found, in the end, is gentler than what he wanted to do with it. Extremes soften. The remarkable becomes ordinary again, not through any punishment or any law, but because the world keeps handing out fresh luck and taking the old luck back, which means that the hard stretches soften too, by the same arithmetic, and for the same reason. Chapter 9, trace something in your head and do not write it down. Just let it happen. Invent a sequence of 20 coin flips. Not real ones, made up by you right now so that they look convincingly random. Heads, tails, whatever comes. Just run through 20 of them. I can tell you two things about what you almost certainly produced. The first is that you alternated too much. You switched from heads to tails far more often than a real coin would, probably a little over half the time rather than exactly half, because every time you had two the same, you felt a small pressure to change. The second is that you avoided long runs. If you produced 4 of the same face in a row, that was probably your maximum, and you likely flinched at it. 5 in a row feels wrong when you are making it up. It feels like you have stopped being random, but a real coin does not flinch. In 100 genuine flips, a streak of 6 or more of the same face turns up more often than not, and even a streak of 7 is not far off even money. If you sat there flipping for a few minutes, you would almost certainly see something that, if you had invented it, you would have crossed out for looking fake. This is the thing nobody tells you about randomness, and it is the source of an enormous amount of confusion. Real randomness clumps. Scatter points at random across a page, and they do not spread out politely. They gather into little knots with bare patches between them. Because nothing is arranging them, nothing is keeping them apart. And there is no rule saying a point may not land right next to the last one. Evenness requires a reason. Clumping is what you get when there is no reason at all, which is exactly backwards from how it feels. When we see a cluster, we assume a cause. When we see an even spread, we assume it just happened. In fact, it is the other way round. An evenly spaced pattern almost always means something is enforcing the spacing. Trees in a dry landscape stand apart because each one is drinking the water around it. The seats people choose on an empty train are spread out because each person is avoiding the others. That regularity is the fingerprint of a mechanism. Let me give you the small classic example, because it is charming. Ladislaus Bortkiewicz was a Russian economist and statistician who, in 1898, published a short book with the wonderful title, The Law of Small Numbers. In it, he looked at the records of the Prussian army over a run of 20 years, and in particular at the number of soldiers killed each year in each corps by being kicked by a horse. It is about as pointless a data set as you could ask for, which is exactly why it works. There is no reason to expect any pattern. Most corps in most years had nobody killed. Some had one, a few had two, a very small number had 3 or 4. And when he compared those counts against what pure chance predicts for rare independent accidents, the fit was almost perfect. The clumping was not a sign that certain regiments kept dangerous horses. It was just what rare events look like when nothing is coordinating them. The mathematics he used had been worked out 60 years earlier by Simeon Denis Poisson in a book of 1837 that was mostly about something else entirely, the reliability of verdicts handed down by juries and judges. Poisson had found the pattern that rare events follow when there are many opportunities for them, and each one is unlikely, and it now carries his name and describes an extraordinary range of things. Calls arriving at a switchboard, mutations in a stretch of copied genetic material, cars passing a quiet junction at night. There is a much more somber example, and it settled a real argument. During the later part of the Second World War, South London was hit by flying bombs, and people living there were convinced they could see a pattern. Certain districts were being struck repeatedly, while others nearby were untouched. The obvious conclusion, widely believed at the time, was that the aim was deliberate, that specific areas were being targeted, possibly because of who lived there. In 1946, an actuary published a short paper that did something very simple. He took a large area of South London and ruled it into several hundred small squares of equal size, and counted how many bombs had landed in each one. The distribution matched the pattern of pure chance almost exactly. Squares with nothing, squares with 1, a handful with 4 or 5, in just the proportions that random scattering produces. The apparent targeting was the ordinary clumpiness of randomness, read by frightened people who very much needed it to mean something. That is the whole difficulty in one story. We are pattern-finding animals, and we are good at it, and the ability is not a defect. Noticing that a certain plant makes you ill, or that the herd moves when the wind turns, is how our ancestors stayed alive. A system tuned to catch real patterns will inevitably also catch false ones, and given the cost of missing a real one, it is tuned to err generously, so the machinery runs constantly, and it does not have an off switch, and it does not tell you which of its outputs are trustworthy. You can stop working now, by the way. There is nothing in this that needs solving before morning. The defense against it is not to stop seeing patterns, which you cannot do anyway. The defense is a single question asked afterwards. Did I decide what would count as interesting before I looked or after? Because if you look at a field of scattered data and then draw your circle around the densest bit you can find, you will always find something, and it will always look striking, and it will mean nothing at all. Some cluster has to be the biggest, somewhere has to have the most. Whichever place that turns out to be will have local details you can point to afterwards and call an explanation. The only honest test is to say in advance what you expect and then go and look somewhere new. That is more or less the entire method of modern science, and it is where we are going next. For now, notice how much lighter this makes the world. A run of bad weeks is not a signal. 3 misfortunes close together are not a pattern. They are what a scattering looks like from close up, and the bare patches, which you never notice at all, are just as much a part of it. Chapter 10. The whole method turns on one small idea, and it was worked out properly at a tea party. An afternoon in the late 1920s, at an agricultural research station in Hertfordshire. Scientists standing about on the grass with cups and saucers. A biologist named Muriel Bristol is offered a cup of tea and declines it because the milk has been poured in after the tea rather than before, and she says she can taste the difference. The general reaction is amused, disbelief. But one of the people standing there is Ronald Aylmer Fisher, a small, intense, extremely short-sighted statistician who was at that time quietly reinventing how experiments are done, and his response is not to argue. His response is to ask how you would find out. He built the answer into the opening pages of his book of 1935 on the design of experiments. And the design is worth walking through slowly, because every clinical trial you have ever heard of is a descendant of it. You could hand her 1 cup and see if she gets it right. But she has 1 chance in 2 of guessing correctly. So a success proves nothing. 2 cups is better. 4 is better still. And you could keep adding cups forever without ever quite knowing when you had enough. So Fisher fixes the whole thing in advance. 8 cups. 4 made one way, 4 made the other. She is told, honestly, that there are 4 of each. Her task is to sort them into the 2 groups, and crucially, the order in which the cups are presented is decided at random by an actual physical process, so that no habit or hint or unconscious pattern in the arrangement can help her. That last step is Fisher's real contribution to the world, and it sounds trivial and is not. Randomizing the arrangement is what makes the arithmetic afterwards mean anything at all. Now count. How many ways are there to choose 4 cups out of 8 to be your guess at the milk first group? The arithmetic triangle answers instantly. 70. So, if she has no ability whatsoever and is simply picking a group of 4 at random, she has 1 chance in 70 of getting every cup right. That is a little over 1 in 100. Uncomfortable enough to be worth taking seriously. But look at the next result down. If she gets 6 of the 8 right, meaning 3 of her 4 are correct, there are 16 ways that can happen out of the 70, which is a little under 1 chance in 4. perfectly ordinary luck. So a near miss tells you almost nothing, and only a clean sweep is worth anything. The design decides what would count as evidence before a single cup is poured. That is the point. Underneath it sits the reasoning that runs all of modern experimental science, and it is a strange, sideways sort of logic that takes a moment to sit with. You do not try to prove that she can taste the difference. You assume, as a courtesy, that she cannot. You assume there is nothing there, no effect, no ability, pure guessing. Then you work out how surprising your actual result would be under that assumption. And if the result would be very surprising indeed, you begin to doubt the assumption you started with. That courtesy assumption is called the null hypothesis, and notice what it can and cannot do. It can be made to look uncomfortable. It can never be proved, and it can never be disproved. You are never establishing that an effect exists. You are only reporting that the alternative has become awkward to hold. Fisher needed a rough line for when awkward became awkward enough, and he suggested in an earlier book a chance of about 1 in 20. He offered it as a convenience. He said elsewhere, quite plainly, that no working scientist has a fixed level year in and year out, and that the sensible thing is to consider each case on its evidence. That casual suggestion hardened into law, and it has caused a great deal of trouble. Here is the first problem, and you have met it already tonight. A result that would be unlikely if there were no effect is not the same thing as a result that makes an effect likely. That is exactly the inversion from earlier, wearing a lab coat. Whether the effect is probably real depends also on how plausible it was before you started, and a great many published surprises were never very plausible to begin with. Here is the second problem. Run 20 honest tests on 20 things that have no effect at all, and on average one of them will cross the line. Not through fraud, through arithmetic. Now imagine thousands of researchers running many tests each, and imagine that the ones that cross the line are the ones that get published, while the others go into a drawer. The published record fills up with the flukes. By the 2010s, this had become a real crisis of confidence. A large collaborative effort, published in 2015, attempted to repeat around 100 well-known psychology experiments. Carefully, with the original authors consulted. Fewer than half came out the same way. Similar exercises in other fields found comparable trouble. Nothing about this means the method is broken. It means the method was being used as a ritual rather than as reasoning. The responses have been sensible and mostly boring. Say in advance what you are going to test and how, so you cannot quietly change the target afterwards. Use bigger samples. Report how large the effect is, not merely whether it crossed a line. Publish the results that came to nothing. Repeat things. That is the immune system of science working, slowly and in public, which is not a comfortable thing to watch, and is exactly what you want to be happening. It seems fair to say that Fisher himself was a complicated figure. He held views on human heredity that most of his field abandoned long ago, and late in life he argued publicly against the link between smoking and lung cancer while doing paid work for the tobacco industry. His technical argument, that a correlation might be produced by some common underlying cause was one he had every right to make, and which he had spent his career teaching others to make. He was wrong about this particular case, and the tools he built are what settled it. You may let all of this go now. It is far past the point where any of it needs your attention. And as for Muriel Bristol, the account usually given is that she was presented with the cups and that she identified every one of them correctly. Fisher does not tell us in the book. He uses the story to make his point and moves on to the mathematics, without ever mentioning how it came out, which is either admirable restraint or a small failure of manners, depending on your mood. She was a scientist in her own right, working on algae, and she married one of the men who was standing on the lawn that day. The cups were real. The tasting was real. And out of one afternoon of politely testing whether somebody's odd little claim might be true, we got the shape of nearly every experiment that has been run since. Chapter 11. We have to go back now and pick up the loose thread I left hanging much earlier in the night, because by the beginning of the 20th century it had become embarrassing. Probability was being used everywhere. In physics, where the behavior of gases had been explained entirely in terms of the statistics of unimaginable numbers of molecules. In biology, in the study of inheritance, in insurance, in astronomy, in the design of experiments, enormous, serious structures were resting on it, and nobody could say what it was. The old definition was the one we started with. Favorable cases divided by all cases, provided the cases are equally likely, which contains the word likely inside the definition of likelihood. It is a circle. You can walk around it comfortably for a very long time without noticing, and people did for 250 years. In 1900, in Paris, the German mathematician David Hilbert stood up at a congress and set out a list of problems he thought the coming century should solve. The sixth of them asked for the mathematical treatment of physics to be built on proper foundations, and he named probability specifically as one of the subjects that needed it. The answer came in 1933, in a slim book of about 60 pages, written in German by a Russian. Andrei Nikolaevich Kolmogorov was born in 1903 in difficult circumstances. His mother died giving birth to him, and he was raised by her sister. He grew up to be one of the great mathematicians of the century, working across an extraordinary range from turbulence in fluids to the mechanics of planetary orbits, and he cared deeply about teaching, running problem sessions for school children for much of his life. His solution to the foundations problem is startling in its simplicity, and the trick is to stop asking the question everyone had been asking. Do not ask what a probability is. Ask what a probability does. Write down the rules it must obey. Take those rules as the definition and build everything on top of them without ever saying what the numbers mean. There are 3 rules, and I can give you all of them in ordinary speech. The first, every event you can talk about gets assigned a number, and that number is never less than 0. The second, the event which is certain, the one that covers everything that could possibly happen, gets the number 1. The third, if 2 events cannot both occur, then the number for one or the other happening is simply the two numbers added together. That is the entire foundation. Everything in this subject, every theorem we have discussed tonight, and thousands we have not, follows from those three statements. What makes it more than a tidying up exercise is what it connects to. Those rules are exactly the rules that mathematicians had already worked out for measuring things. For assigning a length to a stretch of line, an area to a patch of surface, a volume to a region of space. That whole apparatus is called measure theory, and it had been developed for entirely different reasons in the decades before. Kolmogorov's insight is that a probability is a measure. It is a way of assigning size to possibilities, where the total size of everything is 1. And the moment you say that, the entire toolkit of modern analysis, built for other purposes by other people, becomes available. Problems that had been intractable dissolved. Questions that could not previously be stated precisely became ordinary. Now, here is the part I find genuinely lovely, and it is the reason this comes so late in our night. Kolmogorov's axioms do not tell you what probability means. He knew that perfectly well and said so. He had given the subject a rigorous skeleton and had deliberately declined to say what the flesh was. So the question is still open. When you say there is a 1 in 6 chance of rolling a 4, what are you actually claiming about the world? There are 3 serious answers, and educated people have been disagreeing about them for a century. The first is the frequency answer, argued most forcefully by Richard von Mises in the 1920s. A probability is what happens in the long run. It is the fraction you would approach if you rolled the die forever. On this view, the number is a fact about a sequence of repetitions out there in the world and nothing to do with anyone's opinion. It is clean, and it has an awkwardness. Nobody rolls forever, and it says nothing at all about single events. On the strict frequency view, the sentence there is a 70% chance of rain. Tomorrow is close to meaningless, because tomorrow happens once. The second answer says, a probability is a degree of belief. It was worked out independently by Frank Plumpton Ramsey in Cambridge and by Bruno De Finetti in Italy. In the 1920s and 30s, Ramsey was a startling figure. He did foundational work in economics, in logic, in philosophy, all of it while very young, and he died in 1930 at the age of 26 after an illness following surgery. His argument runs like this. Your belief in something is not a feeling, it is a disposition to act, and the cleanest way to measure it is to ask what odds you would accept on a bet. Now, suppose your beliefs about various connected events do not obey Kolmogorov's 3 rules. Ramsey and De Finetti showed that if that is the case, someone can construct a collection of bets, every single one of which you would willingly accept by your own stated odds, which together guarantee that you lose money no matter what happens, which is a beautiful piece of reasoning. It says the rules of probability are not a fact about dice at all. They are the conditions for not being incoherent. Follow them or be milked. The third answer, associated with Karl Popper among others, says a probability is a physical tendency belonging to the setup itself. The die being what it is, has a genuine 1 in 6 disposition, whether it is ever rolled or not. That fits our next subject rather better than the others do, and it is harder to pin down precisely. And the honest position, the one you should go to sleep holding, is that this is not settled. What is remarkable is how little the disagreement matters in practice. The same statistician will use frequency language before lunch and belief language after it and get the right answer both times, because Kolmogorov's rules are the same either way. The skeleton is agreed. The argument is about what kind of animal it belonged to. Kolmogorov himself came back to the problem much later. In the 1960s, along with Ray Solomonoff and Gregory Chaitin working separately, he approached randomness from a completely new direction by asking about description. A sequence is random, on this view, if there is no way to describe it more briefly than simply writing it out. A string of 1,000,000 alternating heads and tails can be described in a sentence. A genuinely random string cannot be compressed at all. Randomness becomes the absence of any shorter story, which is, when you turn it over, a rather peaceful definition. It says that some things in the world are not standing in for anything else and cannot be summarized and are simply themselves all the way through. Chapter 12. So here is the question the whole night has been walking toward, and we can finally ask it properly. Is anything actually random? Or is chance only the name we give to our own poor view of things? For most of the history we have covered, everybody assumed the second. Chance was ignorance, and nothing more. Think about the coin again. It is a rigid disk of metal, obeying perfectly ordinary mechanics. If you knew its exact starting position, the precise force and spin of the thumb, the air in the room, the height of the table, you could work out which face lands up. There is no mystery in the coin. The mystery is entirely in the thumb. That is not a thought experiment, incidentally. Percy Diaconis, who was a professional magician before he became a professor of mathematics, built a machine that flips a coin with the same force and spin every time. It lands the same way every time. The randomness of a coin flip is a fact about human hands, not about metal. Pierre-Simon Laplace put the general version of this into words in 1814, and it is one of the most famous passages in science. Imagine, he said, an intelligence that, at one moment, knew every force acting in nature and the position of every object, and that was vast enough to analyze all of it. For such an intelligence, nothing would be uncertain. The future and the past alike would stand present before its eyes. On that picture, probability is a confession. It is a precise, honest, quantitative confession of what we do not know. And if we knew more, it would shrink toward nothing. Every number in this entire subject is a measure of the size of our own blindfold. That was the settled view of educated people for a very long time. Then, in the 1920s, physics took it away. The story arrives through a strange side door. Erwin Schrödinger had written down an equation in 1926 that described how a certain wave evolves, and the equation worked beautifully, predicting the behavior of atoms with startling accuracy. There was only one difficulty. Nobody could say what was waving. Max Born, then at Göttingen, proposed the answer in a paper that same year. The wave is not a physical substance spread through space. The wave tells you the probability of finding the particle in each place when you look. The detail I love about this is that in the paper as first written, Born got the precise relationship slightly wrong and corrected it in a footnote added while the paper was in proof. The rule that governs every prediction of quantum mechanics, the rule by which essentially all modern physics connects to experiment, first appeared as a note at the bottom of a page. He received the Nobel Prize for it in 1954, 28 years later, and the claim being made was of a completely different kind from anything before it. This was not a statement that we cannot know which way the coin will land. It was a statement that there is no fact about it in advance. The atom does not have a decided answer that we are ignorant of. The probability is the whole of what exists. Albert Einstein hated it, and it is worth being fair about why. Because the popular version of his objection makes him sound like a man who could not accept a new idea. And that is not what happened. In a letter to Max Born at the end of 1926, he wrote that quantum mechanics was certainly impressive, but that an inner voice told him it was not the real thing. The theory said a great deal, he wrote, but did not really bring us closer to the secret of the old one. And then the line everyone knows, in which he says that he, at any rate, is convinced that God does not throw dice. His objection was not superstition. It was that the theory looked incomplete to him. He thought there must be further facts underneath, currently hidden from us, which would restore ordinary determinism, and that probability in physics would turn out to be exactly what it had always been, a measure of ignorance. In 1935, with Boris Podolsky and Nathan Rosen, he set out a careful argument that the theory, as it stood, could not be the final description. Niels Bohr disagreed, at length, for the rest of both their lives. The two of them argued at conference after conference, with enormous mutual respect and no resolution whatsoever. For 3 decades, it looked like a question that could be discussed, but never decided. Then, a physicist working at the European Particle Laboratory near Geneva turned it into an experiment. John Stuart Bell published a short paper in 1964, which did something nobody had thought possible. He showed that if there were hidden facts underneath, of the ordinary local kind that Einstein had in mind, then certain measurements made on pairs of particles would have to obey a specific numerical limit, and quantum mechanics predicted that the limit would be exceeded. A philosophical dispute had become a number you could go and measure. The measurements were hard, and they took a long time. John Clauser did an early version in the early 1970s. Alain Aspect performed a much cleaner one in 1982 in France. Anton Zeilinger and others pushed it further, and by around 2015 experiments had closed the remaining technical gaps that a determined skeptic could point to. In 2022, the three of them shared the Nobel Prize in Physics for this work. The limit is exceeded every time by exactly the amount quantum mechanics says, so the simple hope is gone. There is no set of local hidden facts sitting underneath, quietly determining outcomes, waiting for us to get clever enough to see them. Whatever is happening, it is not that. Now, let me be careful, because this is where popular accounts overreach, and I would rather leave you with something true. What the experiments rule out is a specific class of explanation. They do not, by themselves, prove that the universe is irreducibly random. There are serious physicists who hold that everything remains deterministic, and that what we call a random outcome is the branching of the world into versions, all of which occur with our sense of chance coming from not knowing which branch we are in. There are others who keep determinism by allowing influences that are not local. Both of those are consistent with every experiment ever performed. The mathematics is not in dispute. It is verified to more decimal places than almost anything else in science. What the mathematics is describing is still argued about by careful people in good faith a century on. So the honest answer to the question we started with is that we do not know, and that the not knowing is of a much deeper kind than it used to be, which is not a hard thing to carry to bed. Whatever is going on at the bottom of things, it has been going on the entire time you have been lying there, in every atom of the room and of you, and it has never once needed anybody to understand it in order to keep working. Chapter 13. Let us come back down into ordinary life, because while the physicists were arguing about what chance really is, everybody else simply carried on using it and built most of the modern world out of it while the argument went on. Start with something that began in grief. For a long time, selling an annuity was close to guesswork. You hand over a sum of money, and in return you are paid a fixed amount every year until you die. Governments sold these to raise funds, and the English government sold them at the same price to everyone, regardless of age. A man of 70 paid what a boy of 10 paid, which is, if you think about it for even a moment, a way of quietly losing money to the young. The problem was that nobody had the numbers. To price it properly, you need to know, for a person of a given age, how many more years they are likely to have. And that requires records of deaths with ages attached, kept consistently over years for a population that stays put. London had none of that. The bills of mortality did not record ages reliably, and the city was full of people arriving and leaving. So in 1693, Edmund Halley, the astronomer whose name is on the comet, took a set of records from the city of Breslau in Silesia, which had been sent to the Royal Society by a local clergyman. Breslau was smaller, more settled, and its records listed births and deaths by age, month after month, for years. Halley worked through them and built what is essentially the first proper life table. Out of 1,000 people born, how many are still alive at 1 year, at 10, at 25, at 60? And from that, he showed how to calculate what an annuity on a life of any given age was actually worth. It is a document made entirely out of other people's deaths, compiled by a man who never met any of them, and it turned mortality into something you could plan around. Every pension, every life policy, every calculation of what a society will need to support its old descends from that piece of work. That is the strange kindness of this subject. You cannot say anything at all about whether a particular person will still be here in 10 years. That remains completely unknown, and it is right that it does. But you can say, with real accuracy, how many out of 100,000 will be, and that is enough to build institutions that catch people when the unknowable happens to them. The same trick was already being worked out for ships in a coffee house. Edward Lloyd ran a coffee house in London from the 1680s, first near the Thames and later on Lombard Street, and it happened to be where shipping people gathered. Owners, captains, merchants, and the men with money who were willing to carry some of the risk of a voyage in exchange for a fee. Lloyd collected shipping news to draw the trade in, and the arrangement became an institution that still bears his name. The word underwriter comes straight out of that room. A ship and its cargo would be described on a slip of paper, and each man willing to take a share of the risk wrote his name underneath, with the portion he would carry. Nobody could bear a whole ship. Everybody could bear a fraction of many. Now to something you use constantly without thinking about it. American forecasters began putting a number on the chance of rain in the 1960s, and it puzzled people at first, and it still does. What does it mean to say there is a 70% chance of rain tomorrow? Tomorrow happens once. It either rains or it does not. Here is the honest meaning, and it is a promise about the forecaster rather than about the sky. Gather up every day on which they said 70%, hundreds of them, across years. If the forecaster is any good, it rained on about 70% of those days. Not more, and importantly, not less. That property is called calibration, and it is measurable, and it is the only fair way to judge anyone who makes uncertain predictions. It does not ask them to be right. It asks them to know how right they are. Weather forecasters, when they have been studied, turn out to be among the best calibrated people anyone has measured. They get feedback every single day, which is exactly the condition under which humans learn to judge their own uncertainty well. Many other confident professions, given feedback that is slow or vague or never arrives at all, do considerably worse. You can let all of this drift now if you like. None of it is going anywhere. There is one last piece, and it is my favorite reversal in the whole story. In 1946, a mathematician named Stanislaw Ulam was recovering from a serious illness at his home in Los Angeles, tired, not able to work properly, and passing the time laying out hands of solitaire, being who he was. He began to wonder what the chance was that a hand would come out. And, being a first-rate mathematician, he started trying to calculate it, and found it was a thicket of combinations. Far worse than it looked. Then he had the thought that changed scientific computing. Why calculate at all? Why not simply lay out 100 hands, play them, and count how many came out? He had been working at Los Alamos on problems about neutrons wandering through material, colliding and scattering, and being absorbed, and those problems had the same character. Too tangled to solve directly, but easy to describe one step at a time. So instead of solving the equations, you follow one imaginary neutron through its random walk, and then another and another, thousands of times, and look at what the crowd of them does. He told John von Neumann, who saw it immediately, and within a short time, the method was running on the earliest electronic computers. A colleague, Nicholas Metropolis, suggested the name because Ulam had an uncle who used to borrow money from relatives to gamble at Monte Carlo. So the method is called Monte Carlo, and it is now everywhere. It prices financial instruments, models the climate, plans radiation treatment, renders light in animated films, and designs aircraft. And look at what has happened. For 300 years, people used mathematics to understand randomness. Now randomness is used as a tool to do mathematics that cannot be done any other way. The thing that was the problem became the instrument. There is a final small irony worth mentioning. Ordinary computers cannot actually produce random numbers. They follow instructions, and instructions are the opposite of random. What they produce are sequences generated by a rule, which pass every test for randomness anyone can devise, but are entirely determined by their starting point. For most purposes, that is fine. Where it truly matters, in cryptography, people reach for the physical world instead, sampling the thermal noise in a circuit, or the timing of radioactive decays, or in the case of one internet company, a wall of lava lamps in a lobby, photographed continuously, because the churn of wax in oil is not something anybody can predict. We began the night with people trying to squeeze a little order out of tumbling bones. We have ended up building machines whose whole purpose is to manufacture disorder on demand, because we finally understood what it was good for. Chapter 14, which brings us back to your hand and the 2 dice in it. 9 can be made 4 ways. 10 can be made 3. That is the entire difference. And it took our species something like 4,000 years to write it down. It seems worth asking, now that we have been all the way round, why that small fact was worth the wait. Here is what I think it is. What those counters found, without meaning to, was a way of saying something true about a situation you cannot see all of. Every other kind of knowledge we had built up until then demanded a complete view. Geometry needs the whole triangle. Astronomy needs the whole orbit. If you only had part of the picture, you had nothing. And the honest thing was to say you did not know. Probability is the first tool that lets you say something precise, checkable, and genuinely useful while still admitting that you cannot see the whole thing. It does not pretend the fog is not there. It measures the fog, and that turns out to be almost the only situation we are ever actually in. You do not know whether it will rain. You do not know whether the treatment will work for this particular person. You do not know whether the ship comes home, whether the seed grows, whether the atom decays in the next hour. Not one of those is a failure of effort. Some of them are limits of information, and at least one of them, as far as anyone can currently tell, may be a limit of the world itself. So, it is worth separating 2 things that get muddled constantly. Being uncertain is not the same as being ignorant. Ignorance is having nothing. Uncertainty, done properly, is having a shape. It is knowing that the answer lies in this region rather than that one, and knowing how firmly, and knowing what would move you. That is the difference between saying, I have no idea, and saying there is a 70% chance. The second one can be wrong. It can be checked. It commits you to something, and over hundreds of statements, it can be scored, and the person making them can be found to be honest or not. Now, one last idea, and it is the one I most want you to keep. Unlikely things happen constantly, not occasionally, but all day and everywhere. The reason is simple arithmetic, and it goes in the opposite direction from where people's intuition takes them. Something with a chance of 1 in a million is very unlikely to happen to you today. But there are billions of people, and each of them has a great many things happening in a day. So a 1 in a million event is occurring somewhere thousands of times over before breakfast. Percy Diaconis and Frederick Mosteller gave this a name and pointed out that with a large enough number of opportunities, any outrageous thing you care to specify becomes likely somewhere. A woman named Evelyn Marie Adams won the New Jersey State Lottery twice within 4 months in the mid-1980s, and the newspapers reported odds of many trillions to 1. Those odds were correct for one specific named person buying 2 specific tickets, but that was never the right question. The right question is what the chance is that somebody, somewhere, among all the millions of people buying tickets repeatedly over years, wins twice. Statisticians who worked it out found that it was not merely possible, it was expected. It would have been rather surprising if it had never happened to anyone. So, when the improbable thing arrives, and it will, it is not a message. It is not the universe reaching out to you specifically. It is the ordinary output of an enormous number of chances, and you happen to be standing where one of them landed, which is, if you turn it over, a description of you. Consider what had to happen for you to be lying there tonight. A particular cell meeting, a particular cell out of hundreds of millions. And behind that, 2 people meeting who very nearly did not. And behind them another pair and another back through every generation of your ancestors. Each of them surviving long enough. Each of them finding the person they found. All the way back past history, past language, past our species entirely, to single cells in warm water. Every one of those links held. The chance of that exact chain specified in advance is so small there is no useful way to say it. And yet here you are, which is not a miracle and not a message. It is what happens when a process runs for 4 billion years. Everybody alive is an outcome that would have been called impossible if anyone had been there to predict it beforehand. And there are billions of us, and we are all completely ordinary. That is the whole lesson of the night, really. Improbable is not the same as significant, and it is not the same as fragile either. So let it all settle now, knucklebones on a dirt floor, and nobody counting for 40 centuries. A physician in Milan writing the ratio down between 2 passages about cheating. Galileo Galilei explaining to a gambler why 10 beats 9. 2 men writing letters through the summer of 1654 about a game that was never finished, a die that pays 3.5 coins, which no die can ever pay, 25,000 throws, which was more people than lived in the city, a hill that appears wherever small things are added up, a minister's essay in a drawer, 500 false alarms in a crowd of 10,000, 3 doors, and the 2/3 hiding behind one of them, lead shot rattling down through pins, Prussian cavalry horses, 8 cups of tea on a lawn, 3 rules on 60 pages, a footnote added in proof in which the world stopped being certain, a slip of paper in a coffee house with names written under it, and a man laying out one more hand of solitaire because he was too tired to do anything else, all of it the same thing. A way of speaking honestly about what we cannot see. You have spent this whole night not knowing what tomorrow holds, which is exactly the condition every person who has ever lived has slept in. It is the ordinary human situation. The counting does not remove it. It only says, gently, that not knowing has a structure, and that the structure is kind enough to be understood. There is nothing left to work out. Let your breathing go slow. The dice on the table are not going to be thrown tonight, and the odds will keep on being what they are, whether anybody rolls them or not. Ret now. Good night.